For example, let's consider an atom on your screen. Okay, so we have this atom here, okay, with a nucleus and 3 orbits surrounding it. We expect electrons to fill in the orbits, right? But these electrons, when they fill in the orbit, normally they will take the most stable orbit first, and that is the orbit with the least amount of energy, and that orbit is the one closest to the nucleus, and that's this orbit, the first orbit here. So our electrons will fill in these orbits first before proceeding to fill in the outer orbits that have higher energy. Well, these electrons, we can remember, they can move from one orbit to another. So if an electron absorbs energy and jumps from this orbit here to this next orbit, that we can say our atom is excited. Okay, so our atom can give off energy at that point. But if our electrons too can also move from an orbit of higher energy to an orbit of lower energy, at that point we can say our atom is at ground state. Okay, ground state. All right, so let's take a closer look at these orbits. Okay, let's look at these orbits closely. Well, the orbits, this orbit 1, each orbit is represented by a quantum number, and that quantum number we normally depict it with the letter n. Okay, so for our orbit 1, the first orbit, okay, and then that will be our orbit 1. Okay, that's the first orbit, and so on. We can have orbit 2, orbit 3, orbit 4, 5, and so forth, up to 6, okay, and so on. And then each of these orbits is also represented by a letter, okay, and that letter represents the shell, each of the shell. So our first shell, this orbit, is represented by the letter K. The next shell is represented by L, okay, and so it goes M, this M, N, O, O, P, okay, K, L, M, N, O, P. All right, so it's simple so far, right? But it can get more complex. There are sub-levels that are attached to each of these orbits, each of these shells rather, sorry. So these sub-levels are denoted as sub-level S, have another sub-level P, another sub-level D, and another sub-level F. Okay, they are sub-levels of these major shells, these major orbits. Okay, these are sub-levels, and then each of these sub-levels, they have specific number of electrons that they can carry. Okay, they have specific number of electrons they can carry, and each of them, they are attached to each of these major shells. So the S has a sub level of has S, okay, while our L shell has S and P, and then M has S, P, and D. Okay, S, P, and D, S, P, and D, and N has S, P, D up to F. All right, so we're going to look at each of these sub-levels. Like I told you before, each of them has specific number of electrons that it can carry. Okay, so but thankfully there is a formula for that. Okay, so we're going to attach a quantum number known as azimuthal quantum number for each of these sub-levels. We're going to start from 0. So for S, we're going to start from 0, and for this will be 1, D will be 2, and F will be 3. Sorry, F will be 3. Okay, I'm going to clean this. F will be 3. Good. But there is a formula that makes life easier for all of us. We can use that formula to determine which of them, how many number of electrons that each of these sub levels of shells, okay, of sub levels of these shells can carry. So the formula is, let's quickly have a look at it. Okay, this is the formula: 2 into a bracket of 2 times the quantum number attached to the sub level, okay, plus 1. So for our S, we attach the quantum number of 0, right? So it will be 2 into 2 times 0, right, plus 1. Okay, so our S will carry a quantum number of can carry electrons, total number of 2 electrons, right? Now our P, which we are assigned, which has quantum number of 1, so that will be 2 into 2 goes 2 times 1 plus 1. If we solve that, we're going to get 2 times 1 is 2, okay, plus 1 is 3 already, so times 2 will be 6. So our P can carry maximum of 6 electrons. You can also solve for D. We said D has quantum number days. For D we'll substitute 2 here into this place. While for F you can substitute 3 into this. So if you solve for D, you know that D carries a total number of 10 electrons, while F will carry a total number of 14 electrons, right? Very good. So now that takes us back to our previous, what we're talking about. So since K has S as the only sub level, so the total number of electrons that will be found in K will be 2, since S can carry only 2. While L has S and P, okay, S and P. So S can carry 2 electrons, P can carry 6 electrons. So 2 plus 6 is 8. So our L shell can carry 8 electrons, while the M shell that has sub level S, P, and D, S and P is already 8, and D is 10 electrons. So this can carry a total of 18 electrons. And then the N that has S, P, D, and F can carry a total of S, P, D is already 18 plus 14. That will be can carry a total of 32 electrons. Now the next question, the question you'd want to ask is, how are these electrons arranged in this orbit? Okay, how are they arranged? Actually, there is a rule for the arrangement of these electrons, and that rule is known as the Hofbauer's rule. Okay, so we're going to employ the Hofbauer's rule. Now let's go. Here we go. Good. So we have this. I'm going to change the color. Let's use green. All right, so we have this. Now look at how it's arranged. We have 1s, you write it down this way: 1s, 2s, 3s, 4s, 5s, 6s, 7s. Then you go to the next line and start from 2, the level 2. You write 2p, 3p, 4p, 5p, 6p until you get to 7p. Then you get to the next level. You start from the 3rd level. Okay, you start D, 4d, 3d, 4d, 5d, 6d. So by the time you get to the 4th one, you go down a little. You start at the 4th level for the 4th. So you start 4f, 5f, 6f. And you must note, like we said, the sub levels S, P, D, and F in that direction. Okay, now for you to know which of these comes, how they are arranged around the nucleus, how they are arranged. So we're going to go the rule states that we go this way. So from here, right, diagonal. So we have 1s, then we'll go this way. Next will be 2s, go this way, be 2p and 3s. If we go this way, the next in line will be, after 3s, the next will be 3p, 4s. Then we go this way, right? Then after 4s we'll get 3d, okay, 4p, 5s. And that's how you go from here. You keep going. Okay, you can arrange that. You keep going. That's how it works. Okay, very good. So now we're going to solve some examples. We're going to look at examples of certain elements, and we're going to find out how they are arranged, how the electrons are arranged. Okay, so like I told you before, S can only take 2 electrons. So even if it's 5s, only 2 can go in here, 2 electrons can go in here. Even if it's 1s, only 2 electrons can go in here. So let's solve for, let's say, neon, Ne. Neon has atomic number of 10. Okay, so if neon has 10 electrons has to go in, so the arrangement will be, the first one is 1s, so neon will take 1s2, right? The second is 2s, 2s, s can only take 2, so we have another 2. And 2p, the next is 2p, 2p, p can take 6, so we have 6 here. So if you count it, you have 2 plus 2 plus 6 will give you 10. You see, so this is the electronic configuration of neon. Let's look at something, let's look at calcium. Calcium has 20, right? Atomic number. So for calcium, what we'll have is 1s2, right? Then our 2s will also have 2, right? Then our 2p will have 6. Okay, then after 2p, the next that comes is 3s, so we have 3s, and our 3s will have 2, so we have 12 already. So the next is 3p, p can take 6, so we have 6. Okay, now we have 18 electrons. Then the next is 4s. 4s can take 2, so you see, 2 plus 2 plus 6 plus 2 plus 6 plus 2 will give us a total of 20. So this is the electronic configuration of calcium. Let's look at sodium. Okay, sodium can be written as well. If you put the electronic configuration of neon, right, sodium has 11, right? So you use the electronic configuration of neon, which is 1s2, 2s2, 2p6. Neon is 10, sodium is 11, so we have only one left. Okay, only one atom left to be accounted for. So for that, the next in line after 2p6, from here after 2p, the next is 3s. So sodium we'll create another orbit for sodium, 3s, and then we'll put the remaining one there, 3s1. So this will be the electronic configuration of sodium.